Okay, good morning, ladies and gentlemen. Welcome to this pair distinguished lecture series. You probably know that we organize this distinguished lecture almost about once a month. And today we are very happy to have a Professor Philip Russell to give a distinguished lecture. So let me just briefly introduce our speaker. So Professor Philip Russell is the scientific director of Russell Center for Advanced Light Wave Science in Hangzhou, China. And he's also the founding director of the Max Planck Institute for the Science of Light in Erlangen, Germany, and hold the Krupp Chair in experimental physics at the University of Erlangen, Nuremberg in Germany. So Professor Russell's expertise lies primarily in the field of photonics and new materials, especially the examination of new optical materials. His research interests range from the behavior of light in periodically structured materials to nonlinear optics, waveguides, optical fibers, and their applications. So for over 30 years, Professor Russell has worked on optical crystal fiber, or called PCF, a new pieces of optical fiber that he first proposed in 1991. The PCF was the first demonstrated in 1996, and it has the ability to confine light in hollow cores or with the confined properties not possible in conventional optical fibers. With the PCF, optical fibers have entered in a new era, leading to the breakthroughs and applications in many areas, such as fiber optical communications, fiber lasers, nonlinear devices, high power transmission, highly sensitive gas sensors, and more. Professor Russell obtained his Doctor of Philosophy degree in 1979 at the University of Oxford, the United Kingdom, and has worked in research laboratories and universities in the UK, France, Germany, and the USA. Among the many prestigious honors and awards, Professor Russell has received the 2018 Ranker Prize for optical electronics, the 2015 IEEE Photonics Award, the 2005 Thomas Young Prize of the Institute of Physics, London, and more. He also served as the president of OSA for the year of 2015, which is also known as the International Year of Light. Professor Russell is a fellow of the Royal Society and Optica, formerly known as the Optical Society, and also is a foreign member of the Chinese Academy of Sciences. So without further ado, ladies and gentlemen, please join me in welcoming our distinguished speaker, Professor Philip Russell.
Okay, it all seems to be well set up. But first of all, I'd like to say what a pleasure it is to be back in Hong Kong. It's been quite a few years since I was last here. Nice to see it's still here. I'd also like to thank in particular Professor Wei Jin for nominating me as one of these pair lecturers, and also for the university for agreeing to invite me. So it's a real pleasure to be here. I am planning, I don't want to block the screen, so I'm going to stand at the side. I'm planning to tell you about the history, the story, and the science behind photonic crystal fibers, including some recent results. A lot of this will be quite descriptive. There might be one slide with a bit of mathematics, but some of you, I'm sure, are, you know, don't mind mathematics, but a lot of these things, there's not much in the way of detailed physics. So I'm currently scientific director, as you heard, of this RUSSEL Center in Hangzhou. But the work I'm going to tell you about was carried out in many different places. They're listed on the bottom there. Southampton, University of Bath. Bath is where most of the first breakthroughs were made. then in Germany at the university there and the Max Planck Institute. And then finally, after retirement, you're forced to retire. I didn't want to, but you're forced to retire. I had this wonderful opportunity to help set up this new research center in Hangzhou. Okay, let's get started. That is not a photonic crystal fiber, in case you're wondering. That's a fruit fly. Yeah, doesn't look very happy. It's been put into a scanning electron microscope and had its photograph taken. But it's a strange fruit fly because it's carrying something a bit strange. It stole one of our fibers. It's one of our hollow core fibers. And if you zoom in on that little black dot in the center of the fiber, you'll see this structure, this intricate structure of a periodic lattice of hollow channels. And in the center, there's a hollow core. That was taken by my colleagues at Blaze Photonics Limited, which was a company formed 20 years ago to try and develop telecoms applications of these hollow fibers. But we ran out of money, so sadly. Okay, so how did the idea for photonic crystal fibers arise? Let me tell you a little bit about that. My background at that time in 1991 was in fiber optics partly. I'd worked a lot in fiber optics at the University of Southampton. You know, all of you probably know about optical fibers. In particular, you may have heard of Charles Kao, who did spend time in Hong Kong, but he won the Nobel Prize in 2009 for his proposal that you could use optical fibers for telecoms. Back then, when he proposed this, people laughed at him. They thought this was the most stupid idea. It would never work. How wrong they were. The other component to this was periodic structures that are periodic in space, where you can observe Bragg scattering. This generates beautiful colors in the carapace of beetles and in opals. And of course, this is all explained by the Bragg condition, which the father-son partnership, they won the Nobel Prize for this, and when is about 100 years ago or so. So that's another thing. And then the next thing is the proposal from Jablonowicz that if you design the periodic structure correctly, you might be able to form a photonic bandgap, which is you could completely block the creation of photons in a region of material if you patterned it correctly. I mean, if this pattern of holes and so on in 3 dimensions was appropriate, you could completely turn off light. Light just could not exist. I mean, that's a revolutionary idea. These structures at the top, these have what are known as stop bands, not photonic bandgaps. I get quite angry when I hear people say they have photonic bandgaps up here. It's nonsense. They don't. They have stop bands, good old-fashioned stop bands. If you're an electrical engineer, you've heard of those. What Jablonowicz suggested was revolutionary, that you could create a stop band that was in every direction in 2 dimensions and even 3 dimensions. So I was very excited about this idea at the end of the 1980s. And I got thinking about 2-dimensional photonic bandgaps, which of course should also be possible. Really fascinated by this. So I put these 2 things together, optical fibers, photonic bandgaps, and started to dream a little bit. You know, could we form a fiber with a hollow core that had a photonic bandgap material in the cladding? And if we could do some quite remarkable things. How would this work in practice? Well, that's a side view of this hollow fiber with the photonic bandgap cladding in this particular case. This is the photonic band. And if we send some light in, a ray of light at a certain angle, the likely chance is that it won't be guided. It'll just leak away. If I change the wavelength of light and change the angle, the same thing was quite likely to happen. But if I get the conditions just right, then you will find that the photonic bandgap starts to work and the light just bounces to and fro between the walls of the core, and the light stays guided potentially over long distances. I mean, that was the idea, the original idea. And it seems to me that from back of the envelope calculations that it should work. So that's all very well. But of course, when you have some idea like this, you talk to people, you talk to the experts and see what they think. They were skeptical. Well, to say the least, they were skeptical. One thing they said was that the index contrast, the difference in refractive index between glass and air was too small, was far too small. it's not going to work. You know, this trouble is they hadn't considered out-of-plane propagation when you're propagating not within the plane of the photonic crystal, but actually also along the axis. The fabricators told me, no way this will ever work. It's impossible. You can't, just forget about it. Do something else. You're wasting your time. But they were also wrong. So, now this is, I think, the only plot that I'm going to be showing you. Pretty much almost the only plot. It's a very important plot, though. This is a plot of where the frequency of the light is up here. And this is the propagation constant along the fiber beta. And on this kind of map, we can plot regions where the light is allowed to exist. So in the silica glass itself, it can exist anywhere in this region. So any combination of beta and frequency that lies in this region, light's allowed to exist. But in this region, light can't exist. That's a cutoff region. We can plot the same thing for the hollow regions, the vacuum line. That's where the vacuum line lies. And actually, you also find that there's a special line that delineates the photonic crystal fiber cladding, the periodic lattice of hollow channels. But the most exciting thing back in 1995 was that we discovered, at least John Roberts discovered in his simulations, that there were indeed full two-dimensional photonic band gaps. And most exciting is that these extend into the region where light is free to propagate in vacuum. So here we could have light traveling in vacuum, but unable to escape into the cladding. So we have the perfect conditions for a hollow waveguide. Okay, next question. You can't make it, they said. It's not going to, it's just impossible. There's no way can you do this. Turns out they were wrong. And the technique I tried lots of different techniques initially. Most of them didn't work because no one had made this before. I mean, if nobody's ever made something before, you're never sure if it'll ever work. So we were kind of full of uncertainty and so on. But anyway, we came up finally with this technique, which almost everybody uses these days, which is to stack capillaries. These are about 1 millimeter or a couple of millimeters in diameter. Stack them together very carefully. You put them in a fiber drawing tower and draw them down in size. They all get fused together, about factor of 10 smaller, and then draw it down again to the final optical fiber by a factor altogether, a linear factor of about 100. You can end up with structures that are truly nanoscale with sort of 10 nanometer dimensions that are hundreds of meters long. I think these structures are completely unique. There isn't any other example of a structure like that with such a wide range of scales. Anyway, worked very well. Turns out this technique was first used in the 1970s at Bell Labs by Kaiser and Astle, who were trying to make low-loss guiding cores, and the interstitial points here were the guiding cores in this case. They weren't interested in photonic crystals. They hadn't thought of that. You know, they were working on something totally different, but the technique is more or less the same. Okay, so a little bit of history and the story. The very first photonic crystal fiber that we made, I made with the help of Tim Burks and Jonathan Knight, was the endlessly single mode photonic crystal fiber. And this is not a photonic bandgap material. It's if you replace one of the hollow channels with glass, as is the case here, you can guide light in the solid glass core surrounded by the hollow channels. I mean, it has some interesting features, including guiding only the fundamental modes. This is why we call it endlessly single mode. If you don't have a core of any sort, then you do get accidental guidance or defects in the structure. But when you deliberately put a core in, you get a very nice guidance mechanism. And this turns out to have many applications beyond what you can do with conventional fibers. Okay, another picture from the past. We were very lucky. The three of us moved to the University of Bath. We didn't have any fiber drawing equipment, but we were very fortunate that I met someone from British Telecom Labs, and they wondered if we would like to have a fiber drawing tower. You know, the answer was definitely yes. And it was a 3-legged tower. It was actually, they were intending to send this to the Science Museum in London because it was like, well, you know, sort of a historical thing. But we got it, and most of our first breakthroughs in photonic crystal fiber were made using this equipment. So thanks to British Telecom back then. We had lots of fun in those early days. We made very small core photonic crystal fibers. We made fibers with more complex cores. That's actually a photonic bandgap guiding fiber with a beautiful blue mode. You launch in white light and you get this lovely filtering effect. There's a green version of the same fiber, and these are hollow fibers for photonic bandgap guiding. They tend to take just one of the wavelengths. This is a sort of yellowish color, a pink color. So you get a kind of wavelength filtering in photonic bandgap guidance. Okay, what's it good for? So let's get on to applications. And these applications extend from serious real-world applications to just scientific curiosity and new experiments that you can do. But one of the most exciting things about these fibers is that you can control group velocity dispersion or chromatic dispersion. Let me just talk about this a little bit, some very basic stuff. If you make a hollow waveguide, it's quite straightforward to show that in a hollow waveguide like this, bluer light travels more quickly than red light. Blue light travels more quickly than red. So if you launch in a pulse that has a certain bandwidth, different frequencies, the high frequencies arrive first. So in physical terms, this means that we have anomalous dispersion, and this is entirely a geometrical effect. It's just because the core is a certain size. If you make the core very small, you get very strong anomalous dispersion. Okay. Now let's just think of a bulk material, maybe a gas, a liquid, or a solid material, and you can find many materials that have normal dispersion where the red light arrives first and the blue light arrives afterwards. But obviously, if we fill the core with that material, what you actually get after you've done this, you can't really say what the dispersion is. It depends on the design, because it's the balance between the two effects, the balance between the anomalous dispersion and the normal dispersion that gives you the result at the end. And as I'll show you in a moment, if this is a gas, you can change the pressure of the gas and tune the dispersion. So the ability, just to summarize, the ability to control the magnitude, the sign, and the wavelength dependence of the chromatic dispersion is absolutely vital if you want to control all kinds of nonlinear effects, including supercontinuum generation, which is the next thing I'd like to show you. This is one of the most dramatic results that came out of photonic crystal fiber research. First of all, curiosity, and then this was discovered. This was a team which went to the lab of Alex Gaeta. He was at Cornell at the time. And they just put a short length of photonic crystal fiber. It wasn't made by us. It was a group in the US that made it with a very small core, launched in pulses at 800 nanometer wavelength, invisible pulses. And they saw this dramatic explosion of color, which is called supercontinuum generation. And it's really dramatic and really efficient. The reason it works, well, I go back to what I was discussing a moment ago. The anomalous geometrical dispersion of this tiny core is very strong. So it's able to overcome the normal dispersion of the glass at 800 nanometers. That was impossible to do with standard fibers. All of a sudden, it became possible because of the microstructuring. And that gave rise to this result of supercontinuum generation, which got everybody talking. It was one of the biggest results, I think, in the year 2000 or 1999. Some of the people listening to the talk were people working on optical clocks. These are ultra-precise optical clocks based on, well, you had laboratory after laboratory and chains of frequency conversion experiments. It was very, very complicated. And all of a sudden, you could do the entire experiment on a tabletop with a piece of fiber. So the people working on optical clocks were absolutely amazed by this. It meant that Ted Hensch's idea originally was if you could make an octave spanning femtosecond frequency comb, you could build an optical clock in a very simple way. And for the first time, he was able to do this. PCF made that possible. And this was just shortly before he won the Nobel Prize for this, along with a couple of other people. Okay, what else is it good for? It's another one of my favorite little topics, which came about just by thinking, maybe what can we do with this that might be fun? Well, if you have a very small glass core, and if these hollow channels are very big in comparison to the size of the core, then you'll have a very big acoustic impedance mismatch between the core and the hollow channels. So in principle, it should be possible to trap an acoustic vibration, an acoustic resonance in the core, and the frequency should be in the gigahertz range. So that was my idea originally. We started working on this, and it's led to all sorts of interesting results. Let me just illustrate why this is interesting. So here's the kind of fiber we're working with. It's a 2-micron diameter core, glass core. These are hollow channels. You can see that you get a very nice guided optical mode in the core, but you also get acoustic resonances in the core. And the frequency here is 1.88 gigahertz, it turns out. So this is like a little quartz oscillator, but very high frequency compared to, say, a tuning fork that you would find in a watch. So if you launch a train of pulses into this core with the correct time spacing between them, and if the frequency of this train corresponds with the frequency of the resonance, you can resonantly drive this acoustic vibration, and then it can act back on the light. At least this was my idea at the beginning. And give you some potentially very interesting results. Well, it turned out it worked very well. And just to show you a relatively recent result, this is work by Mung Pang and Wenbin He. So this is a laser which is mode locked at a high harmonic. So instead of just one pulse circulating in the laser, we have hundreds of pulses circulating in the laser. So that's what we call it, high harmonic. There's a length of photonic crystal fiber in the cavity. And this pulse train drives the acoustic wave, the acoustic resonance, and then the acoustic resonance acts back on the pulses. And it turns out it's able to keep the pulses separated by the same amount in a very stable way. We were able to generate, for example, pulses as short as 83 femtoseconds, this erbium amplifier in there, very nice pulses at a very high repetition rate of 1.9 gigahertz in this case. Long-term stable. It's a very nice system once you get it running. And they have been continuing to explore all the applications of this idea over the years since then. Something else, I've got lots of different little snapshots of what you can do with these fibers. Another thing that I was very interested in was, okay, we have a microstructure in the fiber. What happens if we twist the fiber? What effect does that have? And initially I thought, nothing, it's not going to do anything much. But I got the guys to go in the lab and start playing with it and see what happened. So we're thinking about structures like this. These are pillars in Valencia. They date back a long way, 15th century, but they're chiral. You can see they're chiral, they're twisted. What happens if you make a twisted photonic crystal fiber? So there's a picture. We have a straight fiber on the left and a twisted fiber on the right. And if I think about the mode that's guided in the core, it's going to be non-circular. The mode will not be circular. It'll have kind of spokes that push between the hollow channels. These pink dots are hollow channels. So it's not circular, the mode. So when the light travels along, what would you expect to happen? Well, in the straight fiber, nothing much happens, but in the twisted fiber, the mode is forced to rotate as it travels. It doesn't have any choice. It has to follow the hollow channels. As a result of that, if you launch in linearly polarized light, you get what's known as optical rotation, optical activity, that the direction of the electric field rotates slightly, just a little bit. The mode rotates quite fast. It has to follow the twist, but the electric field of the light rotates a little bit. And this is caused by the fact that left and right circularly polarized modes have slightly different phase velocities. And this causes the linear polarization of the light to rotate quite slowly as it travels. One of the consequences of this is that you can maintain circularly polarized light. So you launch in circularly polarized light, you get circularly polarized light out of maybe 50 meters of fiber, which simply you can't do with standard fibers. It doesn't work at all. So circular polarization states are preserved. So what do we do at this point? Well, we thought we've done supercontinuum generation. We have twisted fiber. What happens if we generate a supercontinuum in a chiral or a twisted photonic crystal fiber? So let me show you the results. This is the supercontinuum spectrum that we obtained both in the twisted and the straight fiber. So the pump is at 1 micron roughly, and this is the supercontinuum we're getting. And measuring the polarization state at the output for launching in left circularly polarized light and right circularly polarized light, the polarization state is very well preserved. This number has to be plus or minus 1 to have perfect circular polarization. And these numbers represent the difference of S3 from 1. So it's just a few percent deviation. So extremely well preserved over the entire bandwidth. So for the first time, we can easily generate a supercontinuum spectrum, very broad supercontinuum, which is circularly polarized across the entire bandwidth. If you do this with the untwisted fiber, the polarization state is all over the place. This is +1 and -1. This is 0.06, and so it's a much smaller range. So it's all over the place. And if we look on the Poincare sphere, for those of you who know about polarization, in the twisted fiber, the polarization state clusters at the poles, the North Pole and the South Pole. Those are regions where you get circular polarization state, whereas in the untwisted fiber, it's all over the place. One other nice application. So what else is it good for? Well, it's good for keeping light tightly focused over long distances, as I've mentioned already, in low refractive index materials. So let's have a look at this. If you focus a laser beam down to a small spot, you get a very high intensity, but only over a very short distance. So it's not very good if you want to have high intensity over long distances. Fiber steps in, and all of a sudden we can keep light tightly focused over very long distances. That's a revolutionary change, step forward in applied physics. You couldn't do this before. There was no way to do this at all. No one could think of a way to do this, so simply at least. So it turns out in this case, the product of intensity and length, the product of intensity and length in the very best hollow fibers is 10 million or maybe 20 million times better than at the focus of a lens. That's a factor of 10 million doesn't often appear in applied physics or photonics. So I expected there to be some quite dramatic results. And even more interesting that's come out of this field is that the evolution of a different kind of hollow core fiber that doesn't guide by photonic bandgap effects. This is what we call the Kagome fiber. It has a Kagome lattice in the cladding and a hollow core in the middle. We discovered this in 2002 in my group in Bath. And the interesting thing was that it guided white light. It didn't just guide one wavelength or one color or two colors or something. It guided all wavelengths with a bit of a higher loss. We did some modeling. It doesn't have a photonic bandgap in the cladding. And we ended up deciding that it was guided by anti-resonant reflection, is what we call it in the cladding. And that the design of the first layer of hollow channels is extremely important. Just the first layer. The rest of it doesn't do anything really. So with that idea, 10 years later, in Moscow, a group came up with this very simple structure of a ring of capillaries around the hollow core. It gave quite high loss, but it was an interesting idea. They called it the revolver fiber for obvious reasons. And then this was followed up with a whole series of results from the University of Bath, from Limoges in France, from Beijing, I think this was a group. And Southampton again had got into the act. And the loss in these very simple structures has astonishingly got down to levels that are less than the very best telecommunications fibers. So we may be on the cusp of a completely new generation of telecommunication systems, long haul. I actually think you can view the guidance mechanism in these structures as being caused by a strong radial stop band. So not a photonic bandgap, but a radial stop band, rather similar to something that Yariv had suggested way back in the 1970s. The latest result from that field, I said the loss was incredibly low. The loss is actually less. There's a picture from the paper, but the loss is less than the very best telecoms fibers in the hollow core fiber. Interesting thing that people find interesting is that the light travels 1.5 times faster. So if you're interested in getting information even more quickly from A to B, that's a useful thing. You get almost complete suppression of nonlinear effects, much lower Rayleigh scattering. That goes as 1/λ⁴, so it's a very, very strong effect. It means that you can't use traditional fibers for telecoms at shorter wavelengths. But the hollow fiber makes it possible to think about doing that. So shorter wavelengths can be used for data transmission in principle in a hollow core fiber. So these are all things I think that could lead to a revolution in telecoms. But let's wait and see. What else is it good for? Well, I've mentioned nonlinear optics. Let me just tell you a couple of things about how these hollow fibers have enabled a new era of gas-based nonlinear optics. So this is the first result we got, again in the early 2000s, an observation of stimulated Raman scattering in hydrogen. So we got a length of hollow fiber. We launched in 532 nanometer pulses, and we got very, very intense Stokes conversion. So you convert the frequency of the light, the color of the light by Raman scattering. These are the hydrogen molecules. There's a vibrational one we're looking at here, and we get red light. We also get blue light because of anti-Stokes. It's called conversion to higher frequency. And we were using a Kagome fiber in this case, guiding white light in the core. So the key point here is that the threshold energy for observing this was 100 times lower than ever seen before in hydrogen, because simply you couldn't do the experiment. You couldn't do an experiment like this. So this was a radical step forward. We got a publication out of it, but the one thing we really liked was this perspective written by Mike Downer. He's in Texas. He said a new era in the nonlinear optics of gases and maybe even plasmas is about to begin. Back then, we were very pleased to have this nice comment, but turns out he was quite right. You know, we've been doing plasmas. We can ionize the gas and closely monitor what happens to the refractive index after ionization and so on. Okay, just overall, if you fill the core with a gas, you've got all these advantages. You've got a much higher product of intensity and length than a focused beam. You can guide a broad band of frequencies. You need that if you work with very short pulses. You have a very low light glass overlap, so the damage threshold is very low. But the most exciting thing I mentioned already is that you can pressure tune the dispersion. So if you fill the core with, for example, argon gas, in this case, you can go from anomalous dispersion over the entire frequency range up to normal dispersion, and you can create a pressure tunable zero dispersion point. And that's absolutely key for what I want to talk about next. By adjusting the pressure correctly, you can set up an experiment like this that we launch in 30 femtosecond pulses at 800 nanometers. And at the side of the fiber, you see nothing much happening, but then at the end, the fiber lights up very brightly. And in fact, what's happening is you're getting a temporal focus there. The pulse is getting compressed. And these are simulations of what's happening. The pulse comes in. It's got a duration of 30 femtoseconds. It suffers soliton effect self-compression down to close to a single cycle duration. And at this point, the bandwidth explodes. You get a massive bandwidth. In fact, the bandwidth extends so far that it goes onto the other side of the zero dispersion line. So now we're in the normal dispersion regime. And in this dispersive regime, we get phase matching, in fact, to deep ultraviolet light in this case. We can efficiently generate deep ultraviolet light in this wavelength region. It's actually a very efficient process. But what's really nice about this is that you can generate very short pulses, and also you can generate ultraviolet light. Let me show you some results. These are results where we used neon gas to generate bands of light down to 140 nanometers in the vacuum ultraviolet. And then by changing to helium gas, which has a higher ionization energy, because we don't want the gas to ionize for this experiment, we could get right down to 110 nanometers or so in wavelength. So why is all this stuff so interesting? Well, in hollow core PCF, you can do extreme pulse compression very easily at pulse energies about 1,000 times lower than in previous experiments. This makes it possible to increase the repetition rate from kilohertz to tens of megahertz, which for many applications is absolutely key. You can also potentially make frequency combs and optical clocks in the ultraviolet. And you can replace large-scale systems with compact tabletop systems using the fiber. And there are many applications in biology, medicine, maybe in some fundamental physics experiments also for these results. So one more topic in nonlinear optics using hydrogen. I want to come back to hydrogen again. And these are experiments that I like to view as nonlinear Raman holography. I'll explain why. And also its use in efficient quantum state up conversion. So close to a zero dispersion wavelength. I've shown you the dispersion changes sign. The curve, what's happened to my yeah. So the curvature of the frequency wave vector plot changes sign. So it's got here on this side, the velocity, the group velocity is lower at higher frequency, and here the group velocity is higher at higher frequency on this side. So we take that dispersion plot. I got quite fascinated by this shape. Let's suppose we fill the fiber with hydrogen, which is Raman active. You pump it at a certain frequency, increase the laser power, and then you get this magic effect of Raman scattering that generates lower frequencies with high efficiency. That's called the Stokes band at a lower frequency. And then what's happening in the gas itself is that you're creating what we call a coherence wave with a certain frequency, which is given by the Raman frequency, and also a certain wave vector that depends on the dispersion of this S-shaped curve. So what's actually happening is shown in this video, that the interference between the pump and the Stokes gives rise to a moving interference pattern that drives the molecular motion. So it creates a coherent molecular vibration pattern, which has low entropy. So that because it's got low entropy, it's basically you can extract that energy as work afterwards if you want to. So we can actually then jump to the other side of the S-shaped curve, make use of this coherence wave, which is now a nonlinear hologram, and use it to convert a signal from a lower frequency to a higher frequency. And this is basically a linear scattering process. It's no longer nonlinear. You're scattering off a moving refractive index grating. So we did experiments in this, of course, and they worked so well, so much, you know, you never expect quite such nice results. But here is the experiment where we create the hologram by pumping with 532 green light. This generates a Stokes, first Stokes and a second Stokes bands. In that process, we create the coherence wave. Then we sent in a broadband signal, this blue curve. This is what we wanted to upshift. And when we have to we tune the pressure so we have phase matching. Then you get an upshifted signal that's an almost perfect copy of the signal that went in. And even more surprising is that the conversion efficiency is around 70% in this case. It's almost perfect. So many applications, I think this has potentially. So one application for this effect, I mentioned already, is to single photon up conversion. So you take a single photon up converted in frequency, and you'd like to maintain its state and not sort of mess up its state. And so the experiment here relies on a source of biphoton pairs. These are pairs of photons that are what we call entangled. So their state is entangled. And they're created actually in a microstructured fiber. We call these Mercedes fiber for obvious reasons. The little core in the middle. You launch in 1064 nanometer pulses in the infrared, and you can generate these two wavelengths of light. We then split them off. So we take the higher frequency signal, send it off here, and we take the lower frequency signal, the 1425 nanometer signal, and use this nonlinear Raman hologram to convert the 1425 up to 8. It's not actually mentioned here, but so we then create a coherence wave. Here's the diagram. We go from 1064 to 1911. That's what's happening with this pump inside the fiber. We then use the hologram to read it out. We put in 1425, and we tune the pressure so that we're able to convert to 894 nanometers. So the 894 nanometer signal is this one, and it's quite close to 849. So the question then is, these are single photons. So we're interested in, is the correlation preserved between these photons? And so you can do this with superconducting single photon detectors and time taggers and so on. The results are very nice. So you have to tune the pressure to get this to work really well. So 70 atmospheres was the right pressure. You have to design the fiber correctly so that it guides all the wavelengths you want. And then at the end, you look at the correlations between these two signals of those different wavelengths, the second order correlation. And in fact, you find that the second order correlation is almost perfectly preserved between the original biphoton pair and the upshifted biphoton pair. So this is the first time I think that people have been able to convert single photons over such a huge frequency difference. 125 terahertz is a big fraction of the basic optical frequency. So my final topic, shouldn't take too long, and then I'm finished. Hollow core fiber, what else is it useful for? Well, of course, right at the beginning, I realized that it's got a hollow core. That means you can put things in it. You know, if you have a solid core, you can't put anything in it after you've made it. But hollow core, very simple, you can put things in. So I was really interested in what would happen if you put a small particle in and use laser light to guide it, to trap it and propel it along. And of course, this has a strong link with laser tweezers. This is Arthur Ashkin, who sadly has passed away, but he finally won the Nobel Prize for his proposal many decades before of laser tweezers. So here's the experiment. So we have, again, the hollow fiber. It doesn't have to be photonic bandgap, but this picture, it happens to be. We arrange to hold a particle just at the input face of the hollow core, and then we turn on the laser light, and it pushes the particle into the core, and gradient pressures hold the particle at the center of the core, and radiation pressures push it along. So you can do this many times, send many particles in. It's propelled by radiation pressure. It's trapped by optical gradient forces. It reaches the terminal velocity when viscous and radiation forces balance. So that was the idea. We demonstrated this in 2002. Actually, Fedor Ben-Abi did this. He did a lot of stuff back then, including this experiment, the very first one at least. But I'm going to tell you about a very recent result, which I describe as backward rocket propulsion of using a single femtosecond pulse. Again, this was a result we didn't expect in the lab, but the idea of the experiment was to trap a particle in the hollow core. You have counter-propagating trapping beams, so you can actually keep the particle at one point, so it doesn't move along the fiber, but it's trapped in the core. And then we send in a single femtosecond pulse from a Ti-sapphire laser, just a single pulse, and observe what happens. Now, that's a picture of the geometry. The particle is a pretty small fraction of the total area of the core. And what we saw was unexpected, or what my postdoc saw was unexpected. The particle jumped back very, very fast by about 2 millimeters and then came to a halt. So you launch the pulse, particle goes boom back and stops about 2 millimeters back. Staying it, you could still see it in the core. You knew where it was. You could see the scattering. Taking a fast video camera, she was able to take a succession of frames and then plot the position as a function of time. So that's this blue curve. So these are microseconds, and it moves back by about 2 millimeters or so. And calculating the velocity, the initial velocity of this backward motion was close to the speed of sound, so very fast for such a small particle. So the question is, what on earth is going on here? Well, actually, we had to scratch our heads and think about this a lot, but it didn't take too long to realize that what was happening was that the light coming in with the femtosecond pulse was getting focused down to a spot on the output face of the particle. The particle was acting like a ball lens. So you got very high intensity here, very high intensity, very high energy density here, which then caused ablation, which blasts material off. So material is blasted off the output face, and the velocity of this ablation process is extremely high. I forget the number, but it's thousands and thousands of kilometers per second. It's kind of crazy speeds. As a result, the particle gets a kick backwards because you have to maintain momentum. Momentum has to be conserved in this process, and this kicks the particle back really very, very fast. We were able to apply some theory to this and get very good agreement for different particle sizes with the actual results that we measured. I find this really interesting because it gives you a means of exploring ablation in small particles. People have looked at this before. The trouble they've had is that they get ablation in the particle, but they can't find the particle afterwards. It jumps away, disappears. And these are very tiny. These are 1 micron in size. You lose a 1 micron size particle, you're not going to find it again. But in the hollow core fiber, it's trapped. It doesn't disappear. You know where it is. You can then take it out afterwards, as we did in this case, put it in an electron microscope and take a look at the damage patterns. So this was a particle that had been hit by 3 pulses. It's got 3 craters. It looks like a small moon. You can see the crater here, and it has nice twofold symmetry in the damage pattern. Of course, that's because the light is linearly polarized, which is exactly what you'd expect. So yeah, very, very, actually the original motivation here was maybe we could coat the inner walls of the hollow core with a material using some approach like this. Obviously it didn't work in this case, but I still think that's a research area that one could pursue. All right, so that's the end of all the stuff I wanted to talk about, but just let me show you some people. This is 3 decades or more than 3 decades of working on this idea. Of course, many people have helped to build the photonic crystal fiber structure, if you like. There's some pictures of them. And here's some real pictures of them, of all the groups over the years at the University of Bath and in Germany, at the Max Planck Institute. Lots and lots of people. You may recognize some of the faces. They're scattered all over the world these days. And then most recently, there's this new group in Hangzhou. That's a picture of us just about a week ago, I think, which is growing in size. Of course, we're setting up from scratch. It takes some time, but I think it's a very exciting new adventure for my former students and postdocs who actually created this opportunity. These are people I worked with in Germany who have gone back to China and have set this center up. So I think that's the end of what I wanted to talk about. Thank you all for coming and listening to me.
Thank you, Professor Russell, for the very exciting talk. Are there any questions from the students? I think a lot of young researchers and students. And yeah.
Thank you very much for the very impressive talk, Professor Philip Russell. My question is mainly about the chiral PCF. Could you please turn to the page of chiral PCF?
Yeah.
Yeah, I can see in the twisted case of the PCF, yeah, the model field seems rotates as it travels along the fiber.
Yeah.
Yeah, so in this case, it is concluded that the circular polarizations can be maintained.
Yeah.
However, I would like to, I wonder if any, if light with arbitrary polarization states is standing in such structures, what we get in the output?
So if you put in an arbitrary polarization state, well, an arbitrary polarization state can always be resolved into a combination of circular polarization states. So you superimpose some right circularly polarized light and some left circularly polarized light with the correct phase relationship and the correct amplitudes. You can create any arbitrary polarization state. So if you launch in an arbitrary polarization state, it will evolve periodically as you go down the fiber. And the period of that will be determined by the difference in propagation constant between left and right circularly polarized modes. Because the eigenmodes of the chiral fiber are circularly polarized. Yeah.
Yeah, circular polarized.
Yeah, if it has to be perfect, by the way. If the structure's imperfect, they will be elliptically polarized, and it gets more complicated.
Yeah. So in this case, if a input light with a linearly polarized, so I see the field rotates as it travels. So
yeah, exactly.
Will it is an effect on the linear polarizations on because it's standing light? Yeah.
Well, because linear polarization is a superposition of left and right circularly polarized light. And the direction of the orientation depends on the relative phase of the left and right circularly polarized light. And that's changing as you go down the fiber because the left and right circularly polarized modes have different propagation constants.
Okay, I see. Yeah.
Yeah. It's the same thing as a birefringent fiber, linear birefringent fiber, because in that case you've got two modes that are orthogonally polarized. In this case, the modes are circularly polarized and they're still orthogonal. Just the analogy is perfect between the two situations. Yeah.
Okay. Additionally, can this mode also carry orbital angular momentum?
Sure. Yeah. Yeah. I mean, if you make the core bigger, it can support OAM modes, and we've worked a lot on that, especially in hollow core fiber, twisted hollow core fiber. We've been able to launch in modes that carry orbital momentum, and actually did some Raman scattering with circularly polarized light and OAM in some recent experiments in hydrogen. So that worked very nicely. So yeah, there's an awful lot of things still to be done. I mean, it's quite early days for these experiments. So anybody wants to get involved, I recommend you get in soon, because it's going to become quite popular, I think.
Yeah. Further, in this case, if these modes carry the OAM, will they suffer from the high leakage loss? Because I see the fiber is highly twisted.
No, I mean, the loss, there's hardly any effect on the loss. You need to design the fiber correctly if you want to guide an OAM mode, because it will have a different propagation constant compared to the fundamental mode. So it needs, you need to carefully design it to get low loss. Yeah.
Yeah. Okay. One more question. How to make this chirally PCF if it's post-processing or pre-processing?
Yeah, I didn't tell you how we made it.
Yeah.
Well, the most common thing is that, you know, we make fibers by drawing them from a preform. I didn't show you any videos of that, but basically you have a glass preform, put it into a furnace, and then you draw the fiber off at the bottom. Okay. So what we do is we spin the preform. It takes quite a lot of fancy engineering to make this work, but you can spin the preform really fast, and then when you pull the fiber off, it has a spin. So we can get a kind of helical pitch, a spiral pitch of we can go down to a few millimeters in pitch, which is more than enough to see these effects. You can also do it afterwards. You can also take hollow fiber or whatever it is, and by scanning a flame along it and spinning the one end, you can create a permanent twist. So you don't have to have a fiber drawing system to do this. You can do it in your own lab if you set up a tapering rig.
Yeah. Will there be any difference, the fiber fabrication from these two ways?
You get much lower loss in fiber fabrication in using the drawing tower. But for many experiments, you only need a short length anyway. So we call it post-processing. You take a fiber and you process it after it's made, you know, make a twist afterwards. Yeah.
Okay, thank you.
Thanks for the questions.
Any other questions? Yeah, I noticed that most of the fiber still mainly made using silicon. Are there any other attempt to use other materials?
We'd love to use other materials, but so far it's proving very difficult to make high quality fibers. We had one fantastic result with a supercontinuum generating fiber made from fluorozirconate glass. And we had this extraordinary supercontinuum which extended right down to 200 nanometers with no sign of damage or anything. It just kept working. And I still don't understand why that worked so well. The trouble is we were unable to get any more of the glass. And the reason was typically commercial. The big company had bought the company that made this glass. And the big company said, we're not selling it to you, you can't have it. So they basically stopped the research, and we haven't been able to find a source of that glass since then. Otherwise, I think there'd be a commercial little box you could buy that would generate supercontinuum right down to 200 nanometers. There is nothing like that at the moment. So there's a commercial opportunity for someone who wants to make some money, but you need to get the glass first. Yeah.
Any other questions?
It's a sad example of how commercial interests can kill off research.
Yeah, but that's quite strange, because if you use that material, you open up a new market. Why do they stop it?
I don't know.
No.
I'm not going to say who it was.
Okay. Yeah. Okay. And you also have done a lot of exciting work using putting gas into the fiber. Yeah.
Mm.
So do you actually have to carefully control the amount of gas because it may affect the loss as well? I mean, you change the nonlinearity, you change the dispersion.
Yeah.
By
There's
changing
almost no effect on the loss.
No.
Because we put the gas into all the hollow channels, and not just the core.
Okay.
If you put it just into the core, you destroy the structure, of course,
Yeah,
because
that's
of the
right.
pressure. But if you put it into the entire structure, all the hollow channels, then there aren't any excess forces. So it's very stable, actually.
Okay.
Yeah, that's not so. Yeah, you need to be careful that the gas is very clean. You know, make sure there's no dust particles or something in the gas.
Any other questions?
Yeah, I can. Yes, thank you. Thank you. Very informative talk. With the optical fibers, people have used polymers to make, polymer optical fibers. I wonder whether it is possible one day to use polymers to make this sort of fibers.
Sure. Yeah, I think there've been a number of groups that have worked on that. I think the main one was in Sydney originally, and maybe now in Adelaide. But I'm not sure if they're still working on polymers, polymer fibers. I mean, you can do it, it works. But so far, there don't seem to have been any big applications for some reason. I mean, you could imagine that polymer fibers would be better for medical applications, for example, where the glass doesn't break. I mean, polymers don't break. But I haven't worked on that myself. I suspect it's more difficult to work with a polymer for reasons to do with the material. Silica is just magic. It's an amazing material. You could do almost anything to it and it sort of ends up as a glass. Yeah. So yes, there has been quite a lot of work on polymer fibers. But so far I haven't seen any big applications. Yeah.
Recently, a lot of excitement about this anti-resident fiber. Yeah.
Mm.
Do you see which one will be the first application? Because I think there's a lot of advantage, like very low loss at certain windows, which is not possible for silicon fiber, and very high power delivery, and you mentioned about the relay scattering. And let's say compare, for example, let's say if you want to do a very high power delivery, what is kind of scale of amount of power you can deliver compared with the large effective, I don't know, the fiber?
I'm not sure what the answer is. You should ask Jens Limpert. He works on this. I mean, he's been using hollow fibers for high power delivery. A lot of groups are doing that. It's becoming almost routine. And for scaling up the power of fiber lasers, they're using photonic crystal fiber sort of designs to keep single mode guidance in the large core, so that you don't have higher order modes. I mean, that's certainly being used for high power lasers. As to which of the hollow core fibers, I mean, this I call it single ring hollow fiber. I don't like this anti-resonant name, because it's not anti-resonant. If it was anti-resonant, there wouldn't be any mode in the core.
Okay.
So anti-resonant reflection is the mechanism, if that's true, or it's a radial stop band. But I mean, those single ring fibers have been around for more than 10 years, and there already are lots of applications for them. We seem to be causing a unpleasant ring. So all these experiments on nonlinear optics were made possible by single ring, amongst others. There are applications where the photonic bandgap guidance mechanism is still very valuable, and that's when you want to have narrowband guidance. You know, if you want to suppress Raman scattering, for example, you can use a narrowband guiding hollow fiber to do that. So we do use bandgap fibers for some experiments. Yeah, more difficult to make, by the way.
Yeah, they are. Yeah. Thank you. Any other questions?
Here, can I?
Okay, when you fabricate the the PCF or the anti-resonant fiber, I found in sometimes the fiber drawing speed is quite high, around 100 meter per minute. Is normal or you also need always a high speed to draw that?
No. Quite often it's going to have to be low speed draw.
Around 10 to 20 or what is that?
Well, I don't know what the numbers are. It
Oh,
depends on
okay.
the experiment. But yeah, well, we obviously do play with the drawing speed and the temperature. And also pressure is very important, the pressure in the different regions of the
Yeah,
fiber
right.
during the drawing process. I mean, the details of that are so different between different types of fiber. It's hard to be general about it. But these single ring fibers, the thin wall capillaries, are relatively easy to make, I have to say. I mean, to make them perfect is always difficult, but
Oh,
I mean, it's remarkably simple. It's amazing that you get such low loss for such a simple structure.
so pressure is more important to control than the drawing speed.
Sorry?
So you assume that the pressure, positive or negative pressure, is more important to control than the drawing
I
speed.
think so, yeah. I mean, if you want to preserve a structure, it's good to draw with high tension and lower temperature.
Temperature,
If
yeah.
you can preserve the complex structure. If you don't care about that and the glass, just let the glass make whatever shape it likes, then you can go to higher temperature and draw more quickly.
Yeah.
Yeah. But yeah, there's so many answers to that question.
Yeah. That's right, yeah.
Yes, I want to ask a question about the hollow core fiber. How to keep the core hollow enough during the day-to-day usage, and you know, maybe the dust or moisture could go into the hole. Or
you have to make sure that stuff doesn't get into the core. You need to seal it, of course. Yeah. Yeah, I mean, that's absolutely, I mean, you can easily build a system where the core is protected from the environment. That's not a problem. You know, we have systems that are working for years in the lab that still work. But you do need to be very, very careful about dust and contaminants, and water is also a problem often. But that reminds me of, I think in about the year 2001 or something, I had a question from a journalist. I think he was in the US. He was writing an article about these fibers. And his question was, said, what happens, you know, you've got these fibers, long haul fibers going onto the ocean, you know, between Europe and the US or something, onto the ocean. What happens if a shark comes by and bites the fiber, the shark, and breaks it, and seawater gets into the hollow channel? So a really funny question.
Okay.
Well, I think you, yeah, that was, he was really worried about this, but I don't think he knew much about cables. You know, they're so well protected from sharks, and I think the early cables attracted sharks because there was a big magnetic field, and they liked the magnetic field, and they'd bite the cables and damage them. But since then, they're now screened, so there's no magnetic field. But yeah, that was a funny question from a journalist, but it's a quite serious question. You do need to be very careful.
Okay, you said the hollow fiber useful for transmit power.
Sure. Yeah.
Yeah, because it's empty, right?
Yeah,
it's
great.
vacuum inside, so no material. If
You could get
pass
very,
the
very
light
high
power, there it's supposed low loss.
Yeah, you get low loss, and damage threshold is very high, so they're excellent for transmitting high powers. And yeah.
Okay. Thank you.
Thank you.
Hello.
Oh, hello
Yeah.
again.
Yeah, again. Yeah. I would like to put up with some questions for the chirally piece, yeah, for the simulation work.
Okay.
Yeah. I know that there is a method that I mean, using the finite element method and combined with the transformation optics. Yeah, we can put it in the helical coordinate system.
Helicoidal coordinate system.
Yeah.
There's a COMSOL. I think COMSOL has that.
Yeah. Okay. In that case, as we know, the helical frame will have an effect on the fiber, on the simulated fiber. Yeah. In this case, how do we, or let's say it is if it is necessary for us to remove that effect brought by the helical flame. Otherwise, it would affect our analysis. I mean, let's say for the propagation constant part, we can remove the corrections.
No, you're absolutely, you have to transform back from, I mean, you do the analysis in the rotating frame. So it's as if you're not rotating, you know, so that's what the helical coil frame does for you.
Yeah.
Then you have to, that's in the helical frame. So you aren't aware that you're spinning, and just, you know, as far as you're concerned, that's up and down, and it's up and down where they, you know, so you understand what I mean.
Yeah.
But transforming back to the laboratory frame, you do have to do that carefully. And it involves a twist rate. It's a very simple transformation, actually, to get back to the laboratory frame. And that's where you see the differences in propagation constant. I mean, in the helicoidal frame, you're propagating along a spiral path, whereas in the laboratory frame, you're propagating along a straight path. And the spiral path is clearly longer than the straight path. So what the transformation does is allow you to go from the helicoidal frame, which has the spiral path, back to the laboratory frame, where you have a straight path, and the geometrical length is different. So that's what the transformation does for you. Yeah.
Yeah, I think it's quite straightforward if the fiber structure is rather simple, but I believe for some very complicated structures, it would be hard to identify the effect of the helical frame.
It's actually a very simple transformation.
Yeah,
it doesn't matter how complicated the structure is; it just works.
Yeah, I mean, let's say I know there is a case of, for example, in your publications, a coreless PCF.
Yeah.
Yeah, I mean, in that case, I noticed that the model field is rather very complicated. So in that case, how to transform the propagation constants of such complicated field into the?
It's very straightforward. So sorry, I mean, it's not complicated at all.
It's not?
No.
Yeah.
I'll put you in touch with my former postdoc, if you like.
We can discuss,
send an email to Yang Chen, he'll explain to you. But it's not complicated.
Yeah, okay.
You're obviously worried about it, but it really isn't complicated.
Yeah, okay. Okay, thank you.
Good question anyway.
Yeah. Okay. If there's no further,
Thank you, Professor. I'm curious about the arrangement of the cross section of the PCF. So I see in most cases it seems to be arranged in a hexagon structure. Is it essential, or I was just wondering, or you could just use other like triangles, squares?
Yeah. It is working. Yeah, and it just turns out that the hexagonal structure typically gives the best results. For some reason, gives you the best guidance and so on. For example, in the fiber in the picture. But if you say if you had some other kind of symmetry, such as square symmetry, you can make fibers using square symmetry, and we did that in the early days, but it doesn't work as well, and you end up with linear birefringence and all sorts of effects that you don't want. Plus the guidance mechanism is weaker. So hexagonal is usually a good choice, except for these single ring hollow core fibers, because there we made fibers with 6 capillaries, 5 capillaries, 13 capillaries. I mean, it's the great thing about the single ring is that it frees you up from having to have six-fold symmetry. Yeah. You can use other symmetries, and you can still make the fiber, and so it's actually very nice to be able to do that.
So you mean for the anti-resonant kind of
for the single ring, we call it single ring of capillaries around the core, can have any kind of symmetry you want. So 7-fold, 8-fold, 9-fold rotational symmetry. Yeah. And that's actually very useful for some applications. Yeah.
So is a result out of simulation and experiment, or we have some theoretical explanation?
We've done all the modeling of that, and also done lots of experiments. Yes, Lots of papers have 5 capillaries, some have 13, depending on the application.
Let's thank Professor Philip Russell another time for the wonderful lecture today. And I would also like to thank Professor Lu Chao, who really been the moderator. And I'd like to thank all the people, no matter you ask question or not, to make this a wonderful lecture today. Thank you very much.